Hello and welcome to Math 1500 Applied Business Mathematics. My name is Mr. Jensen, and we're going to look at videos of the lectures for this course. There will be several lectures throughout. I'm going to be as clear as I can, and I'm really hoping that you watch these videos before working on the homework on WebAssign. For the first section in this course, we want to look at functions and refresh our memory as to what a function is. We're used to seeing equations, y equals 3x plus 2, or y equals x squared minus 5. Those are equations. Those equations are also functions. Now, not all equations are functions. All functions are equations. In a function, it's a special rule where each input has exactly one output. So for example, if I said y squared equals x, okay, so hello, welcome to Math 1500 Applied Business Mathematics through Connecticut State Community College. Throughout this course, I'm going to have a video for each section that will kind of steer you in the way that you should go for this course, the way that I want you to approach the course. In each video, I'm going to explain my understanding of mathematics and how I will also test each topic in this course. So be careful. You're watching this video, so you know I want you to watch the video and not just doing the homework in WebAssign. So I hope you watch each one of them. We're going to begin by talking about functions. What is a function? A function, it's a rule. When normally we say an equation that associates each input with exactly one output. What's an input and an output? So you'll notice below, I have the equation y equals 2x minus 8, where I've written this as an equation because I have y equals. When I write this as a function, I say y is a function of x. Y is a function of x, and that function of x is 2x minus 8. So if I set up the function and I say, okay, if x is 0, what is f of x? Well, that would be 2 times 0 minus 8, which is negative 8. If x is 2, f of 2 is 2 times 2 minus 8, or negative 4. Notice that each time I put 0 in for x, I get exactly one value for y. Okay, so that would be a function. The input, the x values, are the independent variable. The output are the dependent variable. You'll notice over here that for each value of y, the negative 8, the negative 4, the value I get for y depends on the value that I put in for x. Y is the dependent variable. The output is the dependent variable. Something that a lot of people struggle with is domain and range. Okay. The domain is the set of all possible values that your independent variable can take on. What values can you put in for x? The range then is what are the resulting values. So if I look back up at the top, I put 0 in for x, 2 in for x. Those are elements of the domain, the values I can put in for x. The range values are the negative 8 and negative 4, the values that come out for y. Now, something that I've observed in my years teaching mathematics is when we teach linear functions, y equals 2x minus 8, we say what's the domain, meaning what values can x take on? X can be any value. Well, it becomes difficult to limit that then. Okay, so if I have y equals x squared, x can be anything. And we start looking at domain and functions. The domain is all real numbers. The domain is all real numbers. Give me an example where it's not. There are two situations where, especially that we're going to look at in this course, where we want to be careful of the domain. You'll notice, again, the values that x, or the independent variable, can take on are the domain. The possible values that y can take on, or the dependent variable can take on, is the range. In these next two examples, we'll talk about the domain exclusively. It is a rule in mathematics that you cannot divide by 0. And here's something that I tend to give. I spend more time if we were in person in class. But I ask students, what is 15 divided by 3? And the answer is consistently 5. We all know that. I ask why. and very difficult to answer that until I realized that 15 divided by 3 is 5, because 3 times 5 is 15. If I have 15 divided by 0 equals some number, that means 0 times n would have to equal 15, and there is no number that I can multiply by 0 to get 15, or 2, or 6, or anything. So the first issue that we're going to look at with the domain is simply the denominator cannot equal 0. So in this case, I have a denominator of 2x plus 6. That denominator cannot equal 0. And then to solve that for x, subtract 6 from both sides. 2x equals negative 6. Divide both sides by 2. And x cannot equal negative 3. So my domain is that x can be all numbers except for negative 3. Now we're going to write that either using set notation. The domain is the set of x values such that x is not negative 3. Or we can use that using interval notation. X can be anything from negative infinity to negative 3, and then everything from negative 3 to positive infinity. Personally, in this case, I would prefer to use the set notation. If I've got a function like the next one here, f of x equals the square root of 5x minus 10, the value underneath the radical, if I've got the square root of 4, we know that that equals 2. The square root of 9 is 3. We could even do the square root of 2 and get a decimal approximation, and it's approximately 1.414. I could take the square root of 0. That would equal 0. I can't take the square root of negative 1 because there is no number, no real number, that I can multiply by itself and get negative 1. So, in a scenario like this, where we have a value underneath the radical, in this case the 5x minus 10, that value underneath the radical has to be greater than or equal to 0. So I'm going to solve that for x. So I'm going to rewrite that, 5x minus 10 must be greater than or equal to 0. Add 10 to both sides. 5x must be greater than or equal to 10. Divide both sides by the 5. X must be greater than or equal to 2. There's my domain. X can be any value, any number, except it has to be greater than 2 or equal to 2. So my domain is the set of x values such that x is greater than or equal to 2. If I use interval notation, I'm going to use a bracket because x could equal 2, and it can be anything up to infinity. The parenthesis because we can't get to the end of it. Okay? When we talk about domain, we talk about the difference between a natural domain versus a restricted domain. In a case of a natural domain, we're talking about here's an equation that works for all values of x. Okay? In one of my teaching jobs, I have a project where I have kids collect values for homes, the square footage and the price of the home. And we come up with something like f of x equals 162x plus 10,000, where 162 would be the price per square foot. But that doesn't really make sense if I'm talking about a 10 square foot house or a 100 square foot house. So even though a linear function has a natural domain that's all real numbers, in this case, my domain x might be restricted to, say, where x is between 1,000 and 3,000, because all the homes I studied had somewhere between 1,000 and 3,000 square feet. Okay. We can represent functions in a number of different ways. We could just give a table. Okay, we could represent it numerically using a table. Here's a table that looks at Facebook. And I know that most of you are younger than I am, and we consider Facebook to be old person social media. But in 2004, when Facebook started, they started with 0 members, or this is millions. A year later, they had 1 million members. After 2 years, so in 2006, 5.4, and you can see the growth. And this is a function. The number of members on Facebook is a function of time. So I can represent a function using a table. I could represent that function graphically. This is the same data. When Facebook was 0 years old, and the year it started, there were 0 million members. Okay, 1 million, and then after 2 years, 5.5 million. After 3, there were 10 million. So you'll see this is about 5.5, 12. This is 50. In year 4, they had 58 million. In year 5, 150 million. So you can see the graph, and you see the rate at which Facebook grew in popularity. Okay. So I can represent functions numerically in a table, graphically on a graph. I can also represent them algebraically using an equation. F of x equals x squared is a function. Okay. If I'm going to evaluate functions, f of x equals 3x plus 5. To find f of 2, notice instead of f of x, I have f of 2. In place of that x is a 2. So in place of the x, I write the 2. 3 times 2 is 6, plus 5 is 11. F of 2 is 11. Notice in B, we have f of 0. In place of the x, there's a 0. So it's 3 times 0 plus 5, or 5, because 3 times 0 is 0, plus 5 is 5. And I'm just going to keep going. And C, f of negative 3. In place of the x, I'm going to write negative 3. 3 times negative 3 is negative 9, plus 5 is negative 4. So f of negative 3 is 4. These next few is where people start to get a little iffy, wonky. I do the same thing. For f of 0, in place of the x, I wrote 0. For f of 2, in place of the x, we wrote 2. For f of t, in place of the x, I write t. And really, there's nothing to do here because 3 times t is simply 3t. For part E, notice we have f of x plus h. So I'm going to have my f of x, which is 3x plus 5, and I add h. No like terms to combine, so I leave that. In part F, though, notice it's not f of x plus h like it was in part E. We have f of x plus h. So where we had 3x plus 5, in place of the x, we have x plus h. 3 times x is 3x. 3 times h is 3h plus 5. Okay. Number 2 is a different type of function, but to evaluate the function, I'm going to do the same thing. F of 2, I replace the x with 2. I encourage you to be careful here. I've got 2 squared is 4, times the 2 is 8. 4 times 2 is 8, and then we have a minus 5. 16 minus 5 is 11. F of 2 equals 11. F of 0, we have 2 times 0 squared plus 4 times 0 minus 5. So 0 plus 0 minus 5 is negative 5. F of negative 3, again, we have 2 times x squared plus 4 times x minus 5. Okay, 2x squared plus 4x minus 5. To find f of negative 3, we're going to replace those x's with the negative 3. And again, be careful. Negative 3 squared is 9. 2 times the 9 is 18. 4 times negative 3 is negative 12. I'm going to change that plus to a minus because it's a negative 12, and then minus 5. 18 minus 12 is 6, minus 5 is 1. F of negative 3 is 1. F of t, I'm simply going to replace the x's with t's. Again, E is f of x, which is 2x squared plus 4x minus 5, and then we're going to add h to that, and we're done. For f of x plus h, again, notice that the function is 2x squared plus 4x minus 5. And again, in place of the x, we're going to substitute the x plus h. And I will tell you that for purposes of this course, I'm okay right there. If you would like to expand it out, you may. I do not need you to at this point. Okay. A piecewise let's look at this. All functions are equations, not all equations are functions. For example, y squared equals x is an equation, but it's not a function. Okay. Because if I have y squared equals x, and let's just say that y squared equals x, and we'll say that x equals 4, y could either be a positive 2 or it could be a negative 2. Notice that for the one element in the domain x, I would have two elements in the range, so this is not a function. Okay. Very quickly, a piecewise function is a function that's made up of two pieces. I've got the 2x minus 3 and x squared plus 1. Notice also there's restrictions here. I use the top part of the function, the 2x minus 3, for values of x that are less than or equal to 2. I use x squared plus 1 for x values greater than 2. So let me squeeze in some problems here. F of 0. Notice that 0 is less than 2. That means I'm going to use the top part. 2 times 0 minus 3 is negative 3. So f of 0 is negative 3. F of 2, now x is equal to 2. I use the top part when x is less than or equal to 2. So I'm going to use the top part here. I'd only use the bottom part when x is greater than 2. So f of 2 is 2 times 2 minus 3. 4 minus 3 is 1. F of 2 is 1. If I compare that to, say, f of 3, now if x is 3, notice that 3 is bigger than 2. So I'm going to use the bottom part of the function. So it's 3 squared plus 1. 9 plus 1 is 10. So f of 3 is 10. Okay. Now we talked about a function. For a function, for each element in the domain, there's one element in the range. We can use what's called a vertical line test when we look at a graph. Suppose I have a quadratic function that looks like this. We do a vertical line test, and I draw some vertical lines. Can I draw a vertical line that will intersect that graph in more than one place? I cannot. That tells me that for each x value, there's only one y value. If I have a graph that looks like this, notice each vertical line can only intersect the graph in one place. Therefore, this is therefore this is a function. Okay, so this one is a function. This is a function. If I have a graph that looks like this, if I do my vertical line test, which is to take vertical lines, can I draw a line that will intersect this graph in more than one place? Yes, this middle red line crosses that graph in more than one place. So you notice that if x is this value, y could be this value or this value or this value here. This is not a function. Something that I think is extremely crucial is the fact that I can use the vertical line test to test whether something is a function or not. Notice my third bullet point, okay? The vertical line test does not cause this to be a function. If I were to ask, why is this third graph not a function? The correct response is not because it fails the vertical line test. The correct response would be because there is a value of x with more than one y value. This middle graph, it is a function because each value of x for each element in the domain there's only one value in the range. Okay, so I hope that you catch that. Types of functions that we will look at in this course are linear functions. A linear function is going to be a graph that is a line. We're going to look at quadratic functions. Quadratic functions are parabolas. We will look at cubic functions, which look like this. A polynomial function, we'll spend a little bit of time talking about polynomial functions. A polynomial function could be a linear function, it could be quadratic, it could be cubic, it could have a higher degree n, it could be a fourth, fifth, sixth degree. We'll cover more as we go through the course. And finally, we're going to look at exponential functions, which we say it increases exponentially. It increases faster and faster and faster. Okay. We'll look at logarithmic functions. Okay. A logarithmic function will look like this. We'll spend a little bit of time, not much, with rational functions. I'll let you look those up on your own, since we're not going to spend too much time with those in this course. Absolute value functions, we're used to seeing those. They'll look like a V. It's not quadratic because these are straight lines, and they make a sharp point at a V. And a square root function, which starts at 0, 0, and increases. And that's basically the top half of a sideways parabola. Okay, so there's a quick first look into functions, Math 1500, Applied Business Mathematics. I hope you stick with me throughout the course and watch each one of the videos for each second. Thank you very much.